Yes, we are live.
So, good evening, everyone, and good morning, also good afternoon for the people coming from Europe as well as in other foreign countries in the USA, Australia, everywhere. So, welcome you all for this e-seminar series from Interdisciplinary Program in Climate Studies. So, just for the audience, I want to briefly tell about the program. This is a seminar series we started in IDP Climate Studies division since 2013. Since pandemic, we are offering this seminar series in virtual mode. And today we are having Dr. Moetasim Ashfaq from Oak Ridge Laboratory, USA, to give a talk. So regarding the seminar today, I think we have more than 150 plus registrations from different countries, including USA, Germany, Pakistan, Switzerland, Japan, Italy, Nigeria, Ethiopia, Canada, Saudi Arabia, UK, all these things. We have a good representation from academia as well as in NGO and as well as from industry people also, and various universities, central universities, private universities, foreign universities also. This one. So Dr. Moet, he will be giving a talk on Karakoram Himalayas, the climate. I commence once again. Yeah, so the climate dynamics in Karakoram Himalayas. I now welcome Dr. Moet, and I request Professor Subimal Ghosh, the head of the Climate Studies Program, to introduce our guest speaker. Thank you.
Thanks, Raj. On behalf of Interdisciplinary Program in Climate Studies, I welcome you all to this very important e-seminar, which is on hidden pathways, cold season precipitation variability over Asian high mountains by Dr. Moetasim Ashfaq from Oak Ridge National Laboratory. It's my pleasure to introduce my very good friend and collaborator, Dr. Moetasim Ashfaq, who is a climate scientist for the Computing and Computational Sciences Directorate at ORNL. Moet is an atmospheric physicist with training in both physics and atmospheric sciences. He leads the high-resolution regional climate modeling effort at Oak Ridge National Laboratory in the Climate Change Science Institute. He is expert in the use of global and regional climate models and also hydrological models for understanding past, present, and future climate variations in response to the natural and anthropogenic forcings. And his works are actually interdisciplinary, and that create a foundation of a multidisciplinary Earth system modeling framework that enables more comprehensive, rigorous investigation of the challenges posed by climate variability and climate change. In fact, I'd like to say that I have spent a good time with Moet during my stay in 2010 at ORNL for 6 months or 7 months, and I personally learned a lot from him on different regional modeling and related to monsoon. So today it's my pleasure to welcome Moet for this very interesting seminar. Moet, the stage is yours.
Subimal, I couldn't hear you well, so do you want me to go ahead?
Yes, please go ahead. I can hear you, please.
Okay. Thank you very much, Subimal, for the introduction. And Subimal and I have a long relationship, over a decade old now, when he was visiting Oak Ridge National Lab. Also, thank you, Professor Raj, for the invitation, and Shiba for sending constant emails and making sure that everything is on right and organized perfectly. So just to make sure that there are no glitches in my presentation, I actually pre-recorded this talk. So I'm going to run that, and along with you guys, I'm going to listen to it, and then towards the end, if you have questions, you can ask, and I'll answer them live. So let me share.
So, today's topic is not the summer, but the cold season. While for most of the world, this region is more known for its highly anticipated, abrupt, and oftentimes merciless summer monsoon season, the cold season over parts of South Asia and its west-northwestern neighboring region in Central Asia is as important and as complex as the summer monsoon season is over South Asia. And that's what we are going to unravel in today's talk. So let's first look at this region in the global context. I know very first thing that comes in mind after seeing the global topographic map is, oh wow, what a beautiful planet, right? And then look at the mighty mountains in Asia. There is absolutely no comparison. By the way, there are 110 mountains on this planet that reach the sky 7,000 meters above the sea level, and all of them are in Asia. Yes, all 110 mountains. These mountain ranges across Asia are known with different names, including Himalayas, which can be divided in eastern, central, and western parts. And then we have Karakoram and Hindukush in the west, northwest South Asia, and finally Pamir and Tian Shan mountains in the Central Asia. And if you want to take a more up closer look, then this is how they look like. Mighty and breathtakingly beautiful. And these mountains play a key role in contributing to river flow through meltwater to major rivers across South and Central Asia, including Brahmaputra in the east, Ganges in the middle, and Indus in the west side of South Asia. And then we have Amu and Sir Darya in the Central Asia, where snow and glacial melt provides as much as 70% of the water for the river flows. Now, perhaps all of you know very well, and I already hinted a bit earlier too, that for some of these mountains, cold season is the time period where predominant fraction of annual snow or precipitation is received. And this will become clearer once we compare annual cycles of total precipitation and snow across these mountain ranges. So, over Karakoram, Hindukush, Pamir, and Tian Shan mountains, most of the snow and precipitation is received during the cold season. Summers are relatively dry, and especially there is relatively very little snow. Over central Himalayas, the amount of snow is very consistent throughout the year, while most of the precipitation is received during the summer monsoon season, which means that in winter, precipitation mostly falls as snow, while in summer, most of it falls as rain. And over eastern Himalayas, most of the precipitation and snow is received outside of the cold season. Now, note that these estimates are based on a high resolution model ensemble simulations, and therefore magnitudes may not be that accurate, but we expect that the intra-annual variability should be close to what the reality is. Now, the reason why western parts of Asian mountains receive relatively more precipitation in winter than eastern parts is manifested once we look at the processes that are responsible for precipitation distribution during the cold season. So the whole region is under the influence of a subtropical westerly jet that spans all the way from northern Africa and Mediterranean to China. This subtropical jet is very important for the cold season precipitation as it guides the movement of extratropical cyclones or western disturbances that are the key mechanism for distributing remote moisture as precipitation over the region, particularly over the high mountains of Central Asia and western South Asia. However, because these systems enter from the west, most of them dissipate while crossing into Central South Asia when they interact with the topography and relatively warm air mass over the Indian subcontinent, which is quite opposite to what happens during summer when most of the monsoon depressions enter from the Bay of Bengal, move west-northwestward, and dissipate by the time they reach western edge of South Asia. Among the natural modes of climate variability that have an influence on cold season precipitation over this region, and so is the most prominent forcing. Perhaps you may know that ANSO propagates its influence through an eastward moving Rossby wave that originates over the equatorial central Pacific. Regions with anomalous high pressure centers associate negatively with ANSO, while regions with anomalous low pressure centers associate positively with ANSO. Earlier studies suggest that cold season precipitation over the high mountains of Asia have positive association with ANSO, which means that during El Nino or positive phase of ANSO, the region experiences more precipitation, and during La Nina or negative phase of ANSO, the region experiences less precipitation. Another internal mode of natural climate variability that has been shown to have an influence over this region is North Atlantic Oscillation, or NAO, which represents fluctuations in the difference of sea level pressure between the Icelandic low and Azores high. Like ANSO, studies suggest that NAO has a positive influence on the precipitation variability over the high mountains of Asia, which again means that during positive phase of NAO, the region experiences more precipitation and vice versa. Earlier studies suggest that positive associations of ANSO and NAO with the cold season precipitation over this region is due to enhanced moisture transport from the surrounding seas, including Arabian, Mediterranean, and Caspian seas. Well, the anomalous moisture transport from these sources during active NAO and ANSO phases may or may not be true, because without actual identification of thermodynamic pathways, these statements remain relatively unquantified. In addition to these two modes of natural climate variability, some studies also suggest that Siberian high may also have some influence on the cold season precipitation variability over the high mountains of Asia. Note that Siberian high is a semi-permanent feature in the northern hemisphere climate with center over Siberia in Russia, which is more active during the cold season, but in my opinion, its role is relatively less understood over the high mountains of Asia. In any case, there are many gaps in our understanding towards these teleconnections over the high mountains of Asia during the cold season. First, because ANSO can exert its influence through several pathways, and I don't think we fully understand the pathways through which its influence over the high mountains of Asia is propagated. Second, like NAO, there are other internal modes of atmospheric variability in the northern hemisphere that can potentially also have influence on the precipitation variability over this region. We know little bit about their influences over Central Asia in general, but not over the high mountains of Asia as a whole. And lastly, all these modes generate atmospheric wave activity. So it is highly unlikely that they don't interact with each other, but understanding towards these interactions is relatively less robust. So what I'm going to do in next several slides is that I will go over each of these 3 points to see what might be missing in our understanding of cold season climate over this region in particular, and regarding these modes of natural climate variability in general. So let's first start with the potential ANSO pathways. We all know that due to zonal sea surface temperatures contrast in the tropical oceans, we have Walker circulation. If we just focus on the Pacific and Indian Oceans, Walker circulation has its rising branch in the warm pool region of Western Pacific, Eastern Indian Ocean, and subsiding branches in the Eastern Pacific and Western Indian Ocean. The rising branch of Walker circulation represents regions with convection, and subsiding branch represents opposite conditions. Now, what happens during the ANSO? Let's just take an example of warm phase of ANSO, which is also known as El Nino, when Central Pacific sea surface temperatures have positive anomaly. These warmer than normal temperatures give rise to anomalous convection in the Central Pacific, which disrupts background Walker circulation, and as a result, we now have anomalous subsidence over the warm pool region of Western Pacific, Eastern Indian Ocean, and anomalous rising motion or convective activity over the Western Indian Ocean. Now, if we just focus on the Indian Ocean sector, these anomalies mean that during positive phase of ENSO, Eastern Indian Ocean receives lesser than normal precipitation, while Western Indian Ocean receives greater than normal precipitation, meaning that a dipole of precipitation anomalies emerge. And of course, opposite conditions prevail during the negative phase of ENSO. Now, let us take this precipitation dipole pattern over the highlighted regions in the Indian Ocean and use it as an index, which can be done by combining the average precipitation anomalies over the two rectangular boxes. We would call it a tropical Western Eastern Indian Ocean Dipole Index, or simply TWEIO. When we regress global precipitation anomalies onto this index, we end up seeing positive association over the Western Indian Ocean, negative association over the Eastern Indian Ocean, and because these anomalies are excited by the ENSO forcing, we also have positive association with the precipitation in the equatorial Pacific, where ENSO-driven sea surface temperature anomalies emerge. We also note that our precipitation index has statistically significant association with precipitation over the parts of Central and South Asia. I am showing this example only for November, but same is true for all cold season months. So what can be inferred from these relationships is that precipitation dipole in the Indian Ocean is forced by the ENSO in the equatorial Pacific via atmospheric link through Walker circulation anomalies, which can be termed as interbasin interaction. But interestingly, TWEIO index also exhibits association with cold season precipitation over the high mountains of Asia. But this relationship of TWEIO in the Indian Ocean to the precipitation over the high mountains of Asia is just a correlative association at the moment, which may not be meaningful unless we demonstrate causative relationship, or in other words, identify those physical mechanisms that remotely link these two regions. Fortunately, today we understand the physical nature of this relationship. We know that the dipole of diabatic heating anomaly caused by the precipitation anomaly dipole in the Indian Ocean also generates an eastward moving Rossby wave through which it remotely teleconnects with regions like the high mountains of Asia. Now, moving on to the second point regarding the potential influence of other internal modes of climate variability, there are several other modes that potentially can influence precipitation over the high mountains of Asia. And why we think that can be the case? Because we know that anything that can influence the position or the strength of subtropical westerly jet would ultimately impact cold season precipitation. And over Atlantic Eurasian sector, there are many more modes that are associated with the atmospheric wave activity. And one of them is East Atlantic mode, which is the second most prominent mode after the NAO. It is structurally quite similar to NAO, but has a southward shift in the anomaly center. I am only showing here is the pattern for December, where it also displays a secondary low over the Western Russia and Central Asia region. Please note that all these NAO, East Atlantic mode, and next indices that I'm going to show here are based on the ones established by the Climate Prediction Center, or CDC. CDC calculates them using empirical orthogonal function analysis on the monthly geopotential height anomalies. And what I'm showing here is the pattern that emerges when you regress monthly sea level pressure anomalies onto these indices. Now, for overanalysis, sea level pressure and any other data sets that we have used is from 3 different reanalysis data sets, including ERA5, ERAI, and MERA2. So let us bring focus back to these other internal modes of variability. The next mode is East Atlantic West Russia pattern, which is the third prominent mode of internal climate variability in the Northern Hemisphere. It reveals negative anomalies over the northern Atlantic and western Russia and positive anomaly over the central Europe when sea level pressure anomalies are regressed onto this index. Lastly, the fourth most prominent mode of variability in the northern hemisphere is called Scandinavian pattern, which features a high pressure cell over Scandinavian part of Europe. So from these patterns, you can easily understand my earlier point that all these modes have the potential to influence the strength and location of subtropical westerly jet over this region and hence the movement or trajectories of the western disturbances. Now, let us get to my last point, which was about the interactions among these interannual and internal modes of natural climate variability. Now, these four modes, including NAO, East Atlantic mode, East Atlantic West Russia pattern, and Scandinavian pattern, all these four modes are orthogonal to each other, given that they are based on the empirical orthogonal function analysis. So we do not expect any correlations among them. However, other three forcings, two from the tropics and one from the extratropics, not only can interact with each other, but also with these other four modes. And as you may all know, the easiest way to detect these interactions is through the simple correlation analysis. So first, we look at the ANSO correlations. As we already know, ANSO directly influences precipitation anomalies in the Indian Ocean via Walker circulation disruption. Therefore, the TWEIO index and ANSO exhibit high correlations in all months, which are all significant. But ANSO also exhibits significant correlations with other internal modes of climate variability, such as with NAO in November, with East Atlantic mode in several months, and with East Atlantic West Russia pattern in December. Interestingly, there is very weak and insignificant correlation between ANSO and Siberian high. Next, we move on to TWEIO correlations. So first line is same as it shows correlations between ANSO and TWEIO, but like ANSO, TWEIO also exhibits correlations which are significant with other internal modes of climate variability such as with NAO, East Atlantic mode, and East Atlantic West Russia pattern in several months. And similarly, like ANSO, there is little to no correlation between TWEIO and Siberian high. This means that these tropical forcings and Siberian high mostly act independently and exhibit little influence on each other. Now, moving on to Siberian high correlations, we note that it exhibits significant negative correlations with East Atlantic mode and East Atlantic West Russia pattern in several months and significant positive correlation with Scandinavian pattern in December. So clearly, there is an indication that these tropical and extratropical forcings interact with other internal modes of natural climate variability. But again, correlations are not very meaningful unless we also identify the pathways through which these relationships are established. So let me show you a few examples to elaborate the physical connections in this regard. And we will do so again by regressing sea level pressure anomalies onto the indices of ANSO, TWEIO, and Siberian high. So let us take an example of Siberian high in February, where it displays strong negative relationship with East Atlantic West Russia pattern. And when we regress sea level pressure anomalies onto Siberian high in February, the pattern that emerges looks like something opposite to what we see in the East Atlantic West Russia pattern, as it exhibits two high pressure centers over North Atlantic and Western Russia and low pressure center over Europe. So looks like Siberian high projects negatively on East Atlantic West Russia pattern in February, and that's why it correlates negatively with East Atlantic West Russia pattern. And to make things clear, let me show you the actual East Atlantic West Russia pattern in February, which is shown here, and which is indeed opposite to what we see in the sea level pressure and Siberian high regression map in the previous slide for this month. Next, let us take an example of ANSO in November, where it displays significantly positive association with NAO. And if we look at its regressed pattern with sea level pressure, we clearly note that emerging pattern bears close resemblance with NAO pattern, meaning that ANSO projects positively on NAO in November, and that's the reason why it has a positive correlation with NAO in this month. And this can be further clarified and demonstrated when we look at the actual NAO pattern in November that is very similar to what emerges from sea level pressure regression onto ANSO in this month. And lastly, let us take an example of TWEIO in December, where it displays significant positive association with East Atlantic mode. And again, we look at its regressed pattern with sea level pressure, we clearly note that emerging pattern bears close resemblance with East Atlantic mode pattern, meaning that TWEIO projects positively on East Atlantic mode in December, and which is also evident when we look at the actual East Atlantic mode pattern in December that is very similar to what emerges from sea level pressure regression onto TWEIO in this month. So this brings us to a point where we can summarize what we have inferred from what I have presented in this talk so far. That is, there are complex and often interacting pathways through which various modes of natural climate variability can exert their influence over a region. In the case of the high mountains of Asia, we note that ANSO can exert its influence directly via Rossby wave that originates over equatorial central Pacific and propagates eastward. It also exerts its influence via interbasin interaction, where ANSO-induced disruption in the Walker circulation leads to a dipolar pattern of precipitation anomalies in the Indian Ocean. These precipitation anomalies cause a dipolar pattern of diabatic heating anomalies in the atmosphere that also generate an eastward propagating Rossby wave, which propagates the indirect ANSO influence via Indian Ocean to remote regions. ANSO can also influence indirectly by projecting on other internal modes of variability such as NAO, East Atlantic mode, and East Atlantic West Russia pattern, which have an influence on precipitation variability over the high mountains of Asia. And fourth way, ANSO can exert its influence indirectly is via interaction of TWEIO with the NAO, East Atlantic mode, and East Atlantic West Russia pattern. Now, of course, ANSO may not be the only reason for dipolar pattern of precipitation anomaly in the Indian Ocean. So we are not necessarily suggesting that whenever there is a TWEIO, it is only because of ANSO. But given high correlation between ANSO index and TWEIO index, one can suggest that ANSO is one of the prominent forcing causing these anomalies in the Indian Ocean. Therefore, the TWEIO influence over any remote region can be termed as ANSO indirect influence. Now, let us not confuse these dipolar patterns in Indian Ocean with Indian Ocean dipole, because Indian Ocean dipole is based on the sea surface temperature anomalies patterns, and Indian Ocean dipole is mostly active in summer and fall season. Whereas here we are talking about the precipitation anomalies patterns, not sea surface temperature anomalies. And also we are talking about these patterns in the cold season. Now, like ANSO, Siberian high also has two pathways. One is direct and one is indirect via its projection on East Atlantic mode, East Atlantic West Russia pattern, and Scandinavian pattern through which it exerts its influence on the precipitation distribution over the high mountains of Asia. And lastly, NAO, East Atlantic mode, East Atlantic West Russia pattern, and Scandinavian pattern can also directly influence the precipitation variability over the high mountains of Asia. Now that we have identified potential modes of variability that can potentially have an influence on the cold season climate over the high mountains of Asia, we want to know the nature of their influences and dynamic and thermodynamic pathways through which they establish these teleconnections. So, we know that any large-scale forcing will create anomalies in atmospheric circulation patterns, and in the case of the high mountains of Asia, it is the changes in the subtropical jet which will subsequently impact the trajectories of western disturbances as well as the frequency of such extratropical systems hitting this region. We also know that such atmospheric anomalies would lead to anomalies in moisture transport. But the dynamical pathway can be easily identified in several ways, for example, by analyzing anomalies in geopotential height, atmospheric winds, velocity potential, etc. However, such analyses are limited when it comes to the robust understanding of moisture anomalies, as winds blowing from a certain region does not necessarily mean that moisture is also coming from that region. And a clear example of this is in the case of summer monsoon in South Asia, where most of the low pressure systems or monsoon depressions originate over the Bay of Bengal, but the moisture in these systems is not necessarily from the Bay of Bengal. In fact, Bay of Bengal is not the major source of moisture compared to what comes from the Arabian Sea, Indian Ocean, and local recycling. Anyway, the discussion about summer monsoon may take us far away from the current topic. So what I'm trying to suggest that if there is anomalous wind blowing from, say, Indian Ocean during active phase of ANSO, it does not establish that excess moisture is also coming from Indian Ocean. And unless we backtrack the moisture that comes over the high mountains of Asia through those anomalous winds, we would not know with absolute authority that excess moisture is coming from the Indian Ocean too. Therefore, what we must do is to establish a robust understanding of moisture sources over the high mountains of Asia. Now, that's the topic that has received relatively less attention, and there are only a couple of recent studies that thus far have focused on this issue. But those studies either are based on a model simulation or short-term data analysis, and also they do not fully cover the whole region encompassing high mountains of Asia. Therefore, a knowledge gap exists when it comes to the identification of moisture sources and their variability during the cold season over the high mountains of Asia, and we have tried to fill this gap in our analysis. Now, I will not go in the technical details of the moisture-backed tracking methodology here, as we do not have sufficient time for that. But you can ask questions at the end if you want to know the details. However, what I would like to let you know is that if we use this evaporative source domain, it tracks back up to 97% of the cold season precipitation to its source. This is shown as a recycling ratio, which is the fraction of moisture falling as precipitation in a specific grid cell that originated as evapotranspiration from the entire source region. So this means that we have been able to track back most of the precipitation that is distributed during the cold season over these high mountains of Asia to its original source. Now, you may notice that we have divided the evaporative source region in 9 subregions. In the black region within these 9 subregions is our region of interest, where cold season precipitation is mostly distributed in South and Central Asia. Now, while every subregion provides moisture, the major contribution comes from the Mediterranean and Caspian Seas, Mediterranean land, local recycling, North Atlantic, and Indian Ocean. The strongest influence of the mid-latitude source regions, such as Mediterranean and Caspian Seas, Mediterranean land, and North Atlantic, are displayed in the west-northwest, which gradually decreases while going from west to east. On the other hand, the strongest footprint of the local recycling is seen over eastern Himalayas, which gradually decreases in its contribution while going west over the Hindukush mountains and beyond. The Indian Ocean contribution is the strongest over relatively dry regions in the southwestern Pakistan and Uttar Pradesh region in India, where it contributes up to 35% of the total seasonal precipitation. Other regions' contribution is relatively low, which is mostly between trace amount to 10%. Now, please note that higher recycling ratio values does not necessarily mean higher precipitation, as it represents the fraction of whatever total amount that was received over that grid point. These moisture contributions from individual sources exhibit intra-seasonal variations. Each line on this panel represents 5-day running mean from a source region, and only those 6 sources are shown whose maxima is at least more than 6% during the season. The shaded area represents the uncertainty across the reanalysis datasets. What you may notice that throughout the cold season, more than half of the moisture comes from the Mediterranean and Caspian Seas and Mediterranean land. The amount of moisture from the Mediterranean and Caspian Seas reduces to almost half of what they contribute in the early part of the season. And in contrast, an increase of 15 to 20% is seen from the Mediterranean land by the end of the season. Up to 50% decline in contribution from Indian Ocean is also witnessed from its peak in January. The local recycling is also the strongest towards the end of the season, while moisture contribution from North Atlantic remains steady throughout the season. So, in a nutshell, there is a persistent dominance of moisture from the mid-latitude evaporative sources, which highlights the importance of western disturbances given that they are the key mechanism for this moisture transport. So, now that we have the way to look at both dynamical and thermodynamical or moisture anomalies that dictate the influence of different modes of natural variability, we can go ahead and identify these patterns. But remember that these modes display interactions among themselves, and therefore, if we want to isolate their influences, we have to remove their impacts on each other. And one way to do so is multilinear regression analysis. Of course, we will not be able to account for any nonlinear interactions among these modes this way, but at least it would give us first-order understanding of their individual isolated influences. But hold on, how do we know that all of these modes exert influence on precipitation variability over the high mountains of Asia? Because it's only me so far who has been trying to sell this story to you without providing any evidence. So let's construct a multilinear regression model step by step and see that how addition of each of these modes in the model helps improve the explained variance of precipitation over this region. So we start with ANSO because it's already well established that it has an influence. The coefficient of determination, or R square, is maximum up to 0.3 in November, but there is not much influence in January and February. Now, we add other modes one by one to this regression model and see whether it improves R square, and indeed we see a gradual increase in its value with the addition of each new independent variable. We also notice an increase in the geographical footprint of the area where F statistics exhibits significance. So this means that all of these modes apparently have a role in the precipitation variability over this region. Now, remember that some of these modes are significantly correlated, although correlations are not extremely high, but still that may cause multicollinearity, right? So we employ variance inflation factor analysis to determine the multicollinearity in the model, and note that the multilinear regression model does not suffer from this issue as variance inflation factor corresponding to all independent variables remains less than 1.5. So using this multi-regression model, we present here the standardized regression coefficients for each month which are comparable with each other. So there are some important details that I would like to highlight. First, TWEIO is the most prominent and persistent forcing throughout the cold season that exhibits statistically significant positive influence on precipitation variability in several months, with the strongest teleconnection in December. Scandinavian pattern is the other forcing that exhibits relatively persistent, though not always significant positive influence throughout the cold season, with exceptions over the parts of Hindukush mountains in November and central Himalayas in January. The strongest, widespread, and statistically significant negative influences are exerted by the East Atlantic mode in December and January over most of the region. Except for Himalayas, East Atlantic mode teleconnection is also negative in February. But we also notice that Siberian high footprints are quite comparable to East Atlantic mode, though relatively subdued during these 3 months, with exceptions over the Himalayas in February. Other modes also exhibit noticeable but spatio-temporally varying influences on the recycled precipitation. And among them, statistically significant negative influences are displayed by ANSO over parts of Hindukush and Pamir mountains in November and December, and by East Atlantic West Russia pattern over the central Himalayas in January. Similarly, statistically significant positive influences come from NAO over the Karakoram, Hindukush, and Pamir mountains in November, and from East Atlantic West Russia pattern over the Hindukush and Pamir mountains in December, and also from Siberian high over the parts of Karakoram, Hindukush, and Pamir mountains in March. So overall, these spatio-temporally varying influences display the complexity of the large-scale teleconnections over this region. It also shows that there is a sub-seasonal variability in these teleconnections, and therefore it is not useful to use seasonal means to establish understanding towards the influences of these natural modes of climate variability. Now, I will take few examples from these teleconnections and explain the thermodynamic and dynamic pathways through which these teleconnections are established. In next few slides, I will show standardized partial regression coefficients from the multilinear regression model for geopotential height, atmospheric winds, and recycled precipitation from individual source regions. The bottom right panel in all these slides will represent the total recycled precipitation anomaly, while other similar panels on the slide will represent the recycled precipitation anomaly from individual source regions. Now, let us first take an example of TWEIO influence in December, and remember that TWEIO represents an index based on precipitation anomaly in the tropical Indian Ocean. It displays the strongest positive association across all months and indices over this region. In December, we note a statistically significant strengthening of subtropical jet, which is represented as negative geopotential height anomalies with anomalous center located over the high mountains of Asia. The pattern of anomalous atmospheric wave train also strengthens the eastward moisture flow over the mid-latitude regions. These atmospheric anomalies lead to a statistically significant increase in moisture supply from all major source regions, including the Mediterranean and Caspian Seas, Mediterranean land, Indian Ocean, North Atlantic, and Northern Eurasia. The strengthening of subtropical westerly jet is also present in January, but with anomaly center now located on the west of the study region that stretches diagonally over the Arabian Peninsula and northern Africa. However, the anomaly pattern over the mid-latitude source regions east of Atlantic now displays slight weakening in the eastward flow. Overall, such atmospheric anomalies favor enhanced moisture transport from the tropical Atlantic, Indian Ocean, and Africa, while slightly reducing the incoming moisture from the mid-latitude regions such as Mediterranean Sea and North Atlantic to the eastern flank of the anomalous low pressure. What is interesting to note between December and January is that in the case of January, contribution from the regions like African land and tropical Atlantic, which normally only provide trace amounts of moisture, is also quite noticeable and statistically significant. So what can be inferred from these comparisons is that while moisture anomalies from major moisture sources play a key role in establishing thermodynamic pathways, role of relatively less important moisture sources cannot be ignored too. Moreover, the strength and nature of teleconnection changes from month to month, as it is the pattern of atmospheric anomalies that dictate where the excess or lack of moisture would come from. The atmospheric anomaly pattern varies month to month, and so does the anomalies in moisture from individual source regions, which in turn dictate the spatial and temporal variability in the teleconnection patterns. Now, one of the strongest and widespread negative influences is displayed by the East Atlantic mode in January, when two statistically significant high pressure centers emerge, one over the study region and one over the Central Europe, which is zonally elongated over the Atlantic sector. These East Atlantic mode induced atmospheric anomalies mutually limit moisture advection over the high mountains of Asia from all source regions, leading to a significant reduction in monthly precipitation. While reduction of moisture from the key source regions play a central role in overall negative association of East Atlantic mode in January, again, relatively less important source regions such as Africa and Eurasia also play a role. Now, let's consider the Scandinavian pattern influence in February, where it induces two zonally connected low pressure cells, one over the East Atlantic and one over the northwest of the high mountains of Asia, which increase moisture advection from the mid-latitude evaporative source regions over the Karakoram, Hindukush, and western Himalayas through the eastern flank of the atmospheric trough, while moisture intrusion from the Indian Ocean is limited over the western flank of the atmospheric trough. And these anomalies overall lead to a positive teleconnection of Scandinavian pattern over those regions. Now, I will provide a couple more examples, and this one is NAO in November, when it exhibits most prominent influence. It displays positive association over northwestern parts and negative association over the rest of the region. This dipolar pattern is due to the fact that it forms a trough over Central Asia that facilitates enhanced moisture transport from the mid-latitude regions, Indian Ocean, and parts of African land to the northwestern parts of the study region, while a ridge appears over the western Himalayas, which reduces moisture supply from the Indian Ocean, African land, and local recycling over those regions. Now, like NAO, the most prominent influence of ANSO is also displayed in November, which is opposite to the pattern of influence exerted by NAO. In the case of ANSO, a low pressure now appears over the western South Asia while a high pressure forms over Central Asia, which limits moisture transport from the mid-latitude source regions to Pamir, Hindukush, and Tian Shan mountains, while more moisture is transported over the Himalayas, especially from the Indian Ocean. Now, I understand that I have quickly rushed through a few of these examples due to a lack of time, but what I really wanted to convey through these results is that the remote teleconnections over the high mountains of Asia are established through a combination of compounding or counteracting dynamic and thermodynamic pathways that are often spatiotemporally superimposed on each other. And with this, we come to the take-home points from everything that I have presented today. So I think the first and foremost point is that there are many natural climate forcings that have an influence on the cold season climate over the high mountains of Asia. And given that several of these modes of variability interact with each other, their impacts cannot be studied exclusively. Secondly, most of these teleconnections vary intraseasonally. Therefore, previously established perspectives on the role of natural modes such as NAO and ANSO in seasonal precipitation variability over the high mountains of Asia are largely equivocal, and incomplete. And in fact, an individual mode can have opposing influences within a season, and that its teleconnection may be a combination of multiple varying pathways. And finally, that a single set of evaporative sources cannot be identified as the only determinant in propagating a remote teleconnection, because nature of moisture anomalies and its sources depends on the pattern of subseasonally varying dynamical forcing in the atmosphere. And lastly, I would like to close by highlighting one important thing that cannot be really ignored, and that is, among all months, February displays large unexplained variance even when we explored the role of 7 modes of natural climate variability. While our analyses are limited in what can be inferred from them in this regard, they provide some clues that may be useful for some targeted analysis in future studies. So, first, what we see that a large portion of the explained variance during the cold season comes from tropical forcing, which is largely absent in February, as ENSO and TWEIO display little influence on the precipitation variability over the high mountains of Asia. And, and secondly, February is the only month with no significant correlation between tropical forcings and mid-latitude atmospheric modes of northern hemisphere, which suggests that the tropical extratropical interactions play a key role in the propagation of planetary scale teleconnections. And and with this, I will stop here and thank you for your attention, and I'll be happy to answer any questions.
Thanks, Moet. I
Thank
think
you,
Shiba,
Dr.
you
Paul.
can start the question answer session.
Yeah. Thank you, sir, for the wonderful presentation. So we do have some 5-7 questions in the Google Sheet, but before that, I would like to ask if any of the participants would want to raise their hands, switch on their videos, and ask questions to Dr. Ashfaq directly. We can do that as well.
Don't know how to raise my hand.
Okay, Professor Raghu, yeah,
I-
please come online.
I'm looking for it, but yeah. Anyway, nice talk, but maybe I should show my face.
Yes, please.
Okay. Thank you. Nice talk, but I got a little bit lost in this alphabet soup of modes, which you said are orthogonal and not related to each other, and yet it's not clear they are really independent. Many of them are kind of known. As you said, East Atlantic mode is kind of a version of the NAO, and then Scandinavian mode and the Russian mode. Looks like there is a way to bring the impact on the subtropical westerly jet and the Rossby waves. Some Rossby waves and western disturbances as the main connection. So the subtropical jet is forced by the tropics and extratropics. And you didn't mention the Arctic, for example. The Arctic has a big influence on the so-called modes, but basically aren't they all functioning through kind of the Western European pressure, high pressure, which navigates the Western disturbances and Rossby waves? So it looks like there could be a unifying theme there rather than this so many regressions and so on. If you just focus on the duration, intensity, and frequency of Western disturbances, because in the end, the moisture source does seem to point to the Western disturbances. So where is the unifying theme possible?
So I think I agree. I got your point that there are multiple modes, but they look like they have similar features, and why not they cannot be unified? I agree, but the way these modes are calculated, these are based on empirical orthogonal function analysis. So, I mean, if you look at the time series, they will not be correlated. It means that within a season, the atmosphere may have these kind of anomalies that when it is in one phase, you call it East Atlantic mode. In another phase, call it NAO. In a third, you call East Atlantic Western shift pattern. So there are different atmospheric wave activity. So, and what I was trying to establish is that, yes, when you have a Rossby wave coming from tropics, it will interact with these this internal modes of variability in the northern hemisphere. So, and because these modes don't coexist, so sometimes the ANSO forcing may project onto one of these modes, and sometimes it may project on some other modes. Now, how these can be unified, I don't think that I can answer that question, but in a general sense, yes, you can say that whenever you have a tropical forcing, that forcing will have an impact on the wave activity in the northern hemisphere. And that because of that, it will have an subsequent impact on, say, the movement of these westerly disturbances, which eventually bring moisture and the precipitation to this region.
Okay. Yeah, thank you. I think Western disturbances probably give a good opportunity to unify, because ENSO, El Nino and La Nina are directly affecting the westerly jet, and then the high latitude forcing is basically being deviated in terms of Rossby waves, have to go around the West European high or can go east directly. So just those two seem to maybe determine the Western disturbance story, which may be a way to unify, I think. Thank you.
And also just want to add that, I understand you also mentioned the Arctic oscillation, but if you look at the NAO and Arctic oscillation, they are quite in phase. So, if you pick one of them, it will have the impact of it.
Yeah, that was kind of
Yes.
my point, because when you talk about ENSO and the Indian Ocean mode, you didn't mention the tropical Atlantic, for example, but it's basically the ITCZ and the subtropical jet that is squeezing the moisture, either from the tropical control or from the extratropical control. But both of them are basically navigating Rossby waves and Western disturbances. So that's how I would see it. But yeah, I mentioned the Arctic because that projects onto all these modes you are mentioning based on what, let's say, the ITCZ is doing. So which one, whether the subtropical high or the Icelandic low will respond or move may depend on these kind of shifts. But anyway, I think others have questions. Thank you.
DJ Rao, you have raised your hand. Would you like to switch on your video and ask your question? DJ Rao?
No, I have not done. Maybe mistake. Sorry.
Okay, fine. So we'll take up the questions from the Google Sheet, Dr. Ashfaq. So here goes the first question. Do the Western Himalayas receive similar patterns of variability for mean and extremes with winter precipitation? We have pasted the question for everyone to see in the chat box as well.
So what was the question? That the Western Himalayas receive
similar patterns
variability?
of variability for mean and extremes winter precipitation?
So I don't think I can answer the question based on the analysis that I presented. So we did not look at any region specifically. Western Himalayas and I'll say Karakoram are kind of mixed region. We didn't look at the extremes. We just look at how the precipitation variability is connected to different large-scale patterns. So yes, because these regions are quite next to each other, so I'll say that whatever is happening over Karakoram should also help partly explain what would happen over the Western Himalayas.
So here goes the second question. Does the Indian Ocean dipole in September have any impacts on the winter precipitation?
So this analysis only focused on from November to March. So we know that Indian Ocean dipole is very active in the summer and in the fall season. So we haven't looked at any lag correlationship. So I'm not aware of any lagged impact of Indian Ocean dipole in September, its subsequent impact on the upcoming winter season.
Here goes the third question. Does the entire series of processes generated from ENSO have any feedback for next year's ENSO?
So again, this is beyond the scope of what I presented. So because see the thing is, we are just focusing on November to March, okay, and then so then there's a big time between March to October. So I don't think I can answer this question with any certainty.
So the fourth question is, can you very briefly discuss your experimental or modeling setup?
So I think you're asking about the moisture source analysis. This is being done through a Lagrangian framework where you backtrack the moisture trajectories in time and space. It's one of the common methodologies. There are two approaches, which is one is Eulerian approach, other is the Lagrangian approach, and this is this approach has been used by Subimal and other folks over South Asia. Basically, just what you do that you take 3D atmospheric moisture and winds and make them 2D by vertically integrating them, and then you go back in time in space from each grid point and see where moisture is coming from, and that's how you backtrack the moisture. But if you want to go into further details, I think the references, for example, the work that Subimal has done or other people have done, you can go and get the details.
Fifth question is, can you infer causality based on regression or correlation?
Correlations, no. I mean, correlation just describes that you have some potential relationship between the two regions, right? Between the two things. Then you have to establish through the physical mechanism. So causality, the way we do it is like, if you are able to say you have, say, ENSO impact over certain remote regions, so you will have a correlation, right? So correlation, then you want to identify the mechanism how that correlation was developed. So yes, say if you do the regression, say with the geopotential, and if you're able to find a wave pattern, Rossby wave pattern, then you may be able to help explain that, yes, this correlation is because ENSO generates a wave, and that wave actually is like high and low pressure cells, and then that's how it propagates its influence. So there are ways, if you look at the dynamical variables and do the regressions, yes, you will be able to establish the physical mechanisms that are basis of those correlations.
So the next question is, can natural aerosols play a role for cold season precipitation in these high mountains?
What I understand, I think the role of aerosol would be much lower. Again, this is a question that I cannot answer with the great confidence. So I will not give a very clear, direct answer. But I think the aerosol impact in the winter climate should be lesser than what it has in the summer climate. But that's something that I have not explored, so I'm not going to comment any further on that.
So yeah, so the questions from the sheet are done. I think Munir wants to ask a question, right, Munir? Can you come online?
Yeah, sure.
I saw your
okay.
hand raised.
Yeah. I like the presentation, the style, and how you have organized the, the figures there, and each summary, how ENSO affects different things.
Mm-hmm. Yes, Munir, you have a question?
Munir, we can't hear you. I think we lost him.
Okay, meanwhile, should I take up the next question or?
Now I can see Munir, I think.
Yeah, I can see him talking, but some network issue.
Yeah.
Maybe he can switch off his camera. Munir, you can switch off. Then we can see it, right?
Munir, can you hear us?
I think his
No.
audio got disconnected somehow. Yeah.
Okay, so there is one question here. What is the primary source of moisture in Mediterranean region that advects towards the study region?
So we did this as a separate study. So in Mediterranean, there are two parts. The Mediterranean goes all the way from the Western Europe to this the Western Asia. So in the western part of Mediterranean, the moisture comes from North Atlantic, whereas the eastern part of Mediterranean, the moisture comes from the Mediterranean Sea. These are the two major sources. And once it comes over the Mediterranean land, then it evaporates, and then it becomes a source again for Western South Asia.
So I think Munir is not back yet. Does anyone else have any question?
Yeah, it's me, Dr. Mubashir from Pakistan. So I would like to thank, first of all, Dr. Moetasim, that you gave such a wonderful talk. I have a question about this regression analysis in which you included so many predictors, such as ENSO, NAO, East Asian, West Russian mode, and several others. So you were mentioning that you dealt with some sort of multicollinearity issue, but I feel that all these modes, especially when we talk about NAO and East Asian, West Russian, and ENSO, so you know that this ENSO sometime could create this NAO pattern through stratospheric pathways. And sometimes this NAO could also be generated in the Atlantic independently. So when you are talking about the direct and indirect influences, so did you dealt with such sort of problems like this NAO could create East Asian, West Russian pattern as well, because they both are strongly connected. I have seen several studies in which they have shown their dependence. So when you put all these predictors, this multicollinearity issue still remains, because I feel that it's not easy to deal with this multicollinearity through multiple regression. We have to design some sort of experiments like a sensitivity experiment in which you first take the condition of ENSO, and then you see if it could create NAO, and in turn this NAO could create East Asian, West Russian. So how you deal with this direct and indirect, and do you think that which effect could be more, like the direct or the indirect, if let's say we talk about ENSO or any other? So how will you answer this?
I think this again relates back to the first question. I think we need to be very clear. So, and at one particular time, and the atmosphere can only be in one state. So these modes will not coexist. So you cannot say today you have an NAO, you also have East Atlantic, West Russia pattern. You cannot have both of them together in the same day. So that's why, that's why when you do this, like try to separate out these modes, which it means that how frequently the atmosphere is in these states. That's how these modes appear. And so at a given time, you only have one mode or the other mode. So that's like the atmospheric wave activity. So the commonality of those modes will make them appear more often. So NAO is the most common mode, East Atlantic will be the second most common, then similarly East Atlantic, West Russian, Scandinavian pattern. All these modes will not coexist at a given time. So the rest of the things that now you mentioned that, okay, I already said, I think in the presentation, I told you that ENSO and any other tropical forcing, even the extratropical forcing Siberian high, they project on these modes, which actually means that you have a wave coming from. So Siberian high also generates a wave, You have ANSO generating a wave, Indian Ocean anomalies generating a wave. So these waves actually, they will interact with the atmospheric dynamics in the mid latitudes, right? And through that interaction, you will end up getting a pattern, one of these patterns, which is the most common pattern in the northern hemisphere. So it's possible, and that's what I also showed, that these modes are going to project onto these modes, the modes that you see in the internal atmospheric dynamics in the northern hemisphere. So what I try to establish is that, yes, you have a Rossby wave coming from, say, tropics. That Rossby wave, if there's no other atmospheric wave activity in the northern hemisphere, that can directly impact a remote region, but it can also enhance, say, the other wave activity, say NAO or other patterns, and because those patterns also have impact on a subsequent downstream region. So that's the indirect way. And then I also showed you the third way, that ANSO also induces anomalies in the Indian Ocean, and that generates a Rossby wave. So all these things. Now, coming to the multilinear regression model, remember, it's a linear regression. It's not a nonlinear regression. For that, we have to do machine learning. So only the linear regression only tells you that, okay, if you isolate everything else, if you remove everything else, what is the isolated impact of one independent variable in that? So as I mentioned while I was explaining the results, is that multilinear regression is one way, but it's not a perfect way. So it's not going to tell you everything, but it at least gives you first order statistics that, okay, the independent influence of this pathway or this independent variable in the multi-regression model, what's its influence on in the dependent variable, which was precipitation in this case.
Thank you very much.
I think you also asked about the multicollinearity. So there are multiple tests, right? We did those tests, and actually you don't expect with these correlations. I showed you correlations, but they were not absolutely high. And you were not like having 0.9 or like 0.8 kind of correlation. So that's why we did not expect to have multicollinearity. And that's why but even then, we have performed tests and we don't see any issue with that. And there's no multicollinearity in the model.
Yeah, thank you very much for the answer.
Thank you. We have one more question in the sheet. So here it goes. We saw a moisture source from northern Gangetic plains. How is moisture from this region transported to western Himalayas in winter, as during winter, the wind direction is southwards over Indian subcontinent?
Yeah, that's right. So there is very trace amount. So I think I try to mention that it's sometimes misleading when you're looking at the recycling ratio. Because say if you have recycling ratio is just a fraction of whatever precipitation amount falls over that grid point, fraction of that, where is it coming from? So the moisture that comes from, say, your central Himalayas and that region, and going that over the western side of the study region, it's very only trace amount. And trace amount is still possible, especially say when you have these kind of atmospheric anomalies, when you have a low pressure and when you have a high pressure, then yes, in those kind of situations, you may have some trace amount moving in the other direction. Otherwise, you know that actually the wind is blowing from west to east. So yes, it's in normal circumstances, it's not possible, but it's not entirely 100% like that. You will never have a moisture going in the other direction. Whenever you have atmospheric anomalies, that always happen every now and then, you will have some trace amount moving in the other direction too. But this is a very trace amount. Trace amount is like maybe negligibly small compared to the other sources.
So we are done with all the questions.
Yeah, thanks, Moit, for such a wonderful presentation and for patiently answering all the questions. It was a wonderful presentation. Thanks a lot for your time. Yeah. Raj here.
Yeah, so thank you,
Thank you.
Dr. Moetasim Ashfaq, for a very wonderful presentation and also nice illustrations describing the different evaporative sources that contribute to the cold season precipitation over high mountain Asia, and also for the very interactive sessions, question answer sessions also. So I'd like to thank you again for accepting our invitation and gave a wonderful lecture. And also I'd like to thank here our seminar coordinating staff, Ms. Sheba, Archishmita and others TA students for helping and conducting this seminar, as well as I'd like to thank Professor Subimal Ghosh for suggesting Dr. Moetasim Ashfaq's name as one of the speaker. So with this, we are coming to the end of this session. So here I'd like to request all the participants to switch on your camera for having a virtual group photo. And also I'd like to announce the next seminar also. The next seminar we are in this series we are going to have on December 1 and 8 by Dr. Navnita Bora from George Mason University. She is going to give a talk on how to communicate science results to the non-experts, because this is a very important aspect, because whatever we are doing, we need to convey to the policy makers and the non-experts to have the impact. So I request all the participants to register for those courses also. The announcement will be made soon. Thank you. So kindly please switch on your camera.
Thanks, Raj.
Yeah, welcome. So Sheba, you can take the.
Yeah, Archishmita ma'am will be taking the pictures.
Yeah.
She takes very good pictures.
So I
Please
request.
switch on your videos, everyone.
Yeah, some are still empty, so kindly switch on.
Yeah, Achanya, Kritika, Debasmita, come on.
I really appreciate Dr. Moetasim, because it's early morning there in USA for him. So thank you once again. Yeah. So done. Yeah. Thank you all. See you in the next seminar. So have a good evening or good day, depend upon the country you are located. Bye-bye.
Thank you, everyone,
Dr. Ashfaq.
for attending. Thanks, Moet.
Yeah.
Thanks, Moet. It was a wonderful talk. Thanks. Bye. Thanks, Raj.
Yeah.
Thanks.
Yeah. See you.
Thanks. And Archishmita. Thanks, everyone, for joining.
Thank you.
Okay. See you.
Thank you. Bye.
Yeah. Shiva, one.